Stuxnet was a highly targeted malware campaign uncovered in 2010 and widely attributed to state actors, designed to sabotage Iran's uranium enrichment program by attacking Siemens' industrial control systems. Unlike earlier cyber operations, it didn't steal data or disrupt networks. It silently manipulated physical machinery, altering centrifuge behavior while feeding falsified sensor readings back to operators. It is widely regarded as the first known government-sponsored cyber attack to cause real, intentional damage to physical infrastructure. Stuxnet is often described as a cyber attack, but that framing misses what actually made it dangerous. It wasn't about breaking encryption or stealing secrets. It was about control, measurement, and deception inside a physical system that operators believed they understood. In this video, we're going to revisit Stuxnet not as a historical artifact, but as a threat model, and ask a more uncomfortable question. If the same attack logic were evaluated under quantum-era assumptions, where sensing, noise, verification, and observability behave differently, what actually changes, what doesn't, and where the real asymmetries emerge? This isn't a story about science fiction malware or quantum computers magically breaking systems. It's about how physical control systems fail when the assumptions underneath them quietly shift. At its core, Stuxnet exploited a system that looked perfectly ordinary. An operator issued commands, a programmable logic controller translated those commands into machine behavior, and sensors reported the physical state of the process back up the chain. Nothing about this architecture was exotic or experimental. It's the standard closed-loop control model used throughout industrial infrastructure worldwide. The critical point is that trust flows upward. Operators trust sensor data, controllers trust measurements, and the entire system assumes that what's observed reflects what's actually happening. Stuxnet didn't break this loop by force. It broke it by quietly inserting itself into the path between control and measurement, leaving the structure intact while subverting the meaning of the signals moving through it. To understand why Stuxnet works so well, it helps to stop thinking of it as a single piece of malware and instead view it as a sequence of coordinated primitives. The first is access. Not just getting onto a network, but reaching the precise control environment where physical behavior is determined. From there comes control, the ability to inject or modify logic that directly governs how the system behaves over time. But control alone is never enough in a physical system, because operators observe outcomes through measurement. That leads to the third primitive, measurement itself. The sensing layer that translates physical reality into digital signals. Stuxnet's real sophistication appears in the next step, deception, where those measurements are selectively manipulated so that what operators see no longer reflects what the machinery is actually doing. Finally, there is verification. The checks, audits, alarms, and confirmations that are supposed to ensure the system is behaving correctly. Stuxnet didn't disable verification, it satisfied it. By attacking these primitives together, access, control, measurement, deception, and verification, the malware didn't need to overwhelm the system. It simply reshaped the story the system was telling itself, allowing physical damage to occur while every layer above believed normal operation was continuing. This is where Stuxnet truly stops looking like malware and starts looking like engineering. What you're seeing here is not chaos, and it's not an obvious override. It's structured control logic, the same kind of ladder and function block logic that runs critical infrastructure all over the world. Inputs arrive from sensors and operator commands, conditions are evaluated, internal states are latched, timers fire, oscillators engage, and outputs are driven in a way that appears entirely legitimate. Every green indicator you see here is telling the system that things are behaving exactly as expected. The key insight is that Stuxnet did not need to rewrite the entire control program. It didn't need to make the system do something wildly out of bounds. Instead, it modified specific paths through the logic, narrow control loops that determine timing, sequencing, and state transitions. By injecting changes at this level, the malware could subtly alter rotational speeds, introduce oscillations, or delay transitions just enough to stress physical components without ever tripping alarms. Notice how layered this logic is. There are checks for running state, stop commands, manual mode, regeneration enable flags, abort conditions, all the things engineers add to make systems safer and more controllable. Stuxnet didn't remove these safeguards. It satisfied them. The logic still evaluated to safe, allowed, and normal, even as the physical process downstream was being driven into regimes it was never designed to tolerate for long periods of time. This is what control without detection really means. From the operator's perspective, the control system was behaving correctly. From the controller's perspective, every conditional branch made sense. From the verification layer's perspective, outputs matched expectations. But beneath all of that, the timing relationships had changed. The system was being pushed, then relaxed, then pushed again. Not violently, not suddenly, but persistently. And that persistence is crucial. Physical systems don't usually fail because of a single dramatic event. They fail because of fatigue, resonance, heat, wear, and microscopic imperfections that accumulate over time. By staying inside the logic and inside the thresholds, Stuxnet allowed damage to accrue invisibly. Nothing here looks like an attack. It looks like a system executing its program. This is why traditional security thinking struggles with attacks like this. There is no obvious signature to match, no corrupted file screaming for attention, no alert that says something is wrong. Control has been altered, but meaning has been preserved. And as long as the system believes its own story, it will continue to operate even as it slowly destroys itself. This is where the real vulnerability lives, and it's not in the control logic or the network path. It's in measurement itself. Every control system ultimately depends on the assumption that sensors provide a faithful representation of physical reality. Rotational speed, vibration, temperature, pressure. These values feel objective, precise, and trustworthy. But they're not reality. They're interpretations of reality produced by sensors that sample, filter, average, and compress physical phenomena into numbers the system can reason about. What you're seeing here is that translation boundary. At the bottom is the physical process. Noisy, chaotic, continuous, and unforgiving. Rotating machinery doesn't move in neat lines. It vibrates, resonates, heats unevenly, and drifts over time. Above it are clean, stable readouts. 9,000 RPM, 1.2 millimeters per second, 75 degrees Celsius. The graphs are smooth. The values are nominal. Everything looks calm. The critical insight is that nothing about these readings is lying. The sensors are reporting exactly what they've been asked to report, at the resolution, frequency, and sensitivity they were designed for. What Stuxnet exploited, and what all cyber-physical attacks exploit, is the gap between what is physically happening and what is observable. By shaping signals before they are sampled, by manipulating timing windows, by replaying previously recorded values, or by exploiting filtering assumptions, an attacker doesn't need to falsify data outright. They only need to ensure that the system never sees the parts of reality that matter. This is why measurement is such a powerful attack surface. Control logic can be audited, code can be reviewed, but measurement is probabilistic, noisy, and incomplete by nature. Sensors don't see continuously. They sample. They don't report raw physics. They report processed signals. And once those signals are smoothed, averaged, or thresholded, entire classes of behavior disappear from view. Stuxnet understood this. Physical damage didn't occur because the system was driven wildly out of bounds. It occurred because the system was driven just inside what the sensors were capable of reliably distinguishing. Stress accumulated in places the instrumentation was blind to. Fatigue grew in regimes that looked statistically normal. The machine was being harmed, but the measurements told a story of stability. This is the uncomfortable truth about cyber-physical security. You don't protect systems by controlling what they do. You protect them by understanding what they can and cannot observe. And once an attacker understands the limits of measurement, they don't need to overpower the system. They can simply operate in the shadows of its perception. Everything we've talked about so far rests on a set of assumptions that are rarely stated out loud, because in classical engineering they're usually safe to make. The first is bounded noise. Engineers assume that fluctuations in sensor readings are small, well-behaved, and confined within known limits. Noise exists, but it's treated as a nuisance, something that averages out over time, not something that fundamentally alters meaning. As long as signals remain inside those bounds, the system believes it understands what's happening. The second assumption is deterministic thresholds. Control systems are built around clean boundaries. Safe versus unsafe, normal versus abnormal. If a measured value crosses a threshold, action is taken. If it doesn't, the system proceeds as planned. This works well when signals are stable and transitions are sharp, but it quietly assumes that thresholds correspond to physical reality, not just to what the instrumentation happens to report. Third is stable sampling. Sensors don't observe continuously. They sample in time. Classical systems assume those samples are frequent enough, evenly spaced enough, and representative enough that nothing important slips through the gaps. If the waveform looks smooth at the sampling points, the system treats it as smooth in reality. What happens between samples is largely ignored. Finally, there is trust in measurement fidelity. Once a signal has been measured, filtered, digitized, and handed to the controller, it is treated as ground truth. Decisions are made downstream on the assumption that measurement accurately reflects the state of the physical system. This creates a straight pipeline. Physical process, measurement, decision, control, with no ambiguity built in. Stuxnet relied on these assumptions not because they were careless, but because they were reasonable in a classical world. Noise was assumed to be bounded. Thresholds were assumed to mean something physical. Sampling was assumed to be sufficient. Measurements were assumed to be faithful. The attack didn't need to violate these assumptions outright. It only needed to operate in the narrow spaces where they begin to weaken. And this is the critical setup point. The danger isn't that these assumptions are wrong. It's that they stop being reliable when sensing becomes probabilistic, when noise becomes dominant, and when the act of measurement itself alters what is being observed. Once that happens, the entire control framework is still running, but it's running on foundations that no longer behave the way engineers expect. This is the point where the assumptions we just talked about quietly collapse, not because engineers made mistakes, but because the underlying physics no longer behaves the way those assumptions require. In a quantum-era sensing environment, noise is no longer a bounded nuisance that averages away. It becomes intrinsic, statistical, and inseparable from the signal itself. What used to be a single measured value is now a probability distribution, and every observation is really a statement about likelihood rather than certainty. Thresholds don't disappear, but they lose their determinism. Crossing a line no longer means something is definitively safe or unsafe, only that one outcome has become more probable than another. Sampling, which once felt passive, now actively disturbs the system being observed, introducing aliasing, backaction, and uncertainty that cannot be filtered out after the fact. Even the act of measurement changes what comes next. And once outcomes depend on how, when, and with what precision a system is observed, the idea of a single, objective ground truth starts to break down. What the controller sees is no longer a faithful snapshot of reality, but one branch among many possible realities shaped by observation itself. This doesn't mean control systems stop working. It means they continue operating while quietly accumulating uncertainty, making decisions based on confidence bands instead of facts, and trusting measurements that are fundamentally probabilistic. And that shift is subtle enough that everything still looks normal, right up until the moment it isn't. This is where the balance quietly shifts in favor of the attacker, not because they're more powerful, but because they understand how uncertainty actually behaves. In a probabilistic sensing environment, detection is no longer a question of whether something crosses a clear line. It's a question of confidence. Defenders don't see absolute values. They see distributions, noise floors, and likelihoods. Somewhere above that noise floor is a region where activity becomes statistically distinguishable, and below it is a region where behavior cannot be separated from normal variation with any meaningful confidence. That lower region isn't empty. It's where attackers live. What matters here is that the attacker doesn't need to hide perfectly. They only need to remain statistically indistinguishable from background noise. By making small, incremental manipulations that stay inside confidence bands, an attacker can apply real physical influence while every individual observation still looks normal. Each change, viewed in isolation, is explainable. Each deviation fits inside expected variance. But over time, those changes accumulate, and the physical system experiences stress, drift, fatigue, or resonance that was never designed to be sustained. Notice how detection becomes probabilistic rather than absolute. There is no single moment where the system can say with certainty, "This is an attack." Instead, there's a rising likelihood that something is wrong, balanced against the cost of false positives. Raise sensitivity too high, and the system triggers alarms constantly. Lower it, and the attacker gains more room to operate. This trade-off is unavoidable because noise is no longer an external nuisance. It is part of the signal itself. This creates a powerful asymmetry. The defender must prove that something abnormal is happening with sufficient confidence to justify action. The attacker only needs to avoid crossing that confidence threshold. And because the attacker controls timing, magnitude, and persistence, they can shape their activity to exploit exactly the regions where detection is weakest. They don't rush, they don't spike, they drift. This is why quantum-era attacks don't look dramatic. They don't announce themselves. They look like systems aging, components wearing out, sensors behaving imperfectly, or environments fluctuating. And by the time the evidence becomes strong enough to act on, the damage has often already been done. The system didn't fail because it was blind. It failed because it could see only probabilistically, and the attacker knew how to live inside that uncertainty. This is where the defender finally starts to regain ground, not by eliminating uncertainty, but by learning how to work with it instead of against it. When individual measurements are noisy and probabilistic, any single sensor or snapshot is unreliable. But uncertainty behaves differently when observations are aggregated across time, space, or independent channels. Each individual signal may sit comfortably inside the noise floor, but when many such signals are combined, correlated structure begins to emerge while uncorrelated noise cancels out. Confidence grows not because the system suddenly sees more clearly, but because repeated observation sharpens statistical resolution. Variance shrinks as observations accumulate, and patterns that were previously indistinguishable from background noise start to rise above it. This is the mathematical counterweight to the attacker's strategy. The attacker relies on operating just below detection confidence at any single moment, while the defender relies on persistence, correlation, and accumulation to reveal what cannot remain hidden forever. The key point is that detection doesn't happen instantly, and it doesn't happen locally. It happens slowly, statistically, and globally. What once looked like harmless drift becomes a structured deviation, what once looked like normal fluctuation becomes an emerging signal, and what once fit comfortably inside confidence bands begins to push against them. This doesn't eliminate false positives or guarantee perfect detection, but it shifts the asymmetry back toward the defender by making time and repetition assets rather than liabilities. In a quantum-era threat model, security doesn't come from sharper thresholds or stronger instantaneous sensing. It comes from aggregation, correlation, and the disciplined accumulation of evidence until probability hardens into conviction. Here we see the most important and least sensational way quantum changes an attack like Stuxnet, and it has nothing to do with breaking encryption or rewriting control logic, because none of that was the limiting factor in the first place. What limited Stuxnet was time and uncertainty. In the classical case, an attacker has to observe a physical system for a long time to infer its internal dynamics, because every measurement is noisy and indirect, and confidence accumulates slowly. That long observation phase is dangerous, because it's where detection is most likely to occur. A quantum-assisted attacker doesn't gain a new capability so much as they compress that phase dramatically. Quantum-enhanced sensing, estimation, and inference tighten confidence intervals faster, meaning fewer observations are required to understand how a system responds to subtle control changes. The same noisy rotor behavior that would take weeks or months to characterize classically can converge statistically much earlier, not because the physics is different, but because uncertainty collapses faster. And that matters because once the attacker understands where the safe-looking but damaging regimes live, the attack stops being exploratory and starts being surgical. Calibration ends sooner, deception begins earlier, and the entire operation spends more time operating inside regions the defender cannot distinguish from normal behavior. The system doesn't become louder or more aggressive, it becomes quieter sooner. That's the real danger here. Quantum doesn't introduce new attack primitives, it shifts the timeline in a way that favors the attacker by reducing exposure during the most vulnerable phase of the operation, and that single asymmetry is enough to make an already effective cyber-physical attack meaningfully more dangerous. This depiction is not about exact historical numbers. It's about a reasonable and defensible way to think about how attacks like Stuxnet actually come together, and how quantum changes the timeline rather than the logic. Any cyber-physical attack of this kind has a learning and calibration phase where attackers have to observe the system, infer its internal dynamics, test responses, and build confidence that small control changes will have predictable physical effects without triggering alarms. In the classical world, that phase is slow because every observation is noisy, correlated, and incomplete, and confidence accumulates painfully over time. A conservative assumption is that this process takes on the order of weeks to a couple of months, not because engineers are incompetent, but because physical systems drift. Sensors lie within tolerances, and you need repeated cycles to be sure you understand what you're seeing. If we take a reasonable midpoint, say 60 days of effective calibration time, and then ask what happens when uncertainty shrinks as 1 over the square root of the number of effectively independent observations, the effect is not magic, it's compression. Even modest improvements in sensing and inference efficiency translate into large reductions in elapsed time. If the effective number of independent observations is only 25, the calibration window drops from 60 days to roughly 12. If it's closer to 100, it drops to around 6. If it reaches 400, it drops to about 3. None of these numbers require exotic assumptions, and all of them still respect real-world correlations that limit how much independent information you actually get. The point is that quantum assistance doesn't eliminate uncertainty. It reduces how long you have to live with it. And that matters because the calibration phase is the most dangerous phase for the attacker and the safest phase for the defender. Compressing it shifts the balance. The attacker reaches high confidence sooner, spends less time probing and exposing themselves, and enters the damage-causing phase earlier and more quietly, while the defender loses reaction time without seeing anything fundamentally new or dramatic happen on the surface of the system. That single shift, time compressed by statistical leverage, is enough to make an already serious attack meaningfully more dangerous, even if nothing else about the attack changes at all. The deeper lesson from Stuxnet is not about a specific piece of malware or a specific era of technology, but about how real systems fail when trust, measurement, and control quietly drift out of alignment. Stuxnet worked because it attacked the assumptions engineers rely on rather than the code they write, exploiting the fact that measurement is always noisy, sampled, and incomplete in cyber-physical systems. Quantum technologies don't change that reality. They intensify it by compressing uncertainty and accelerating inference, allowing attackers to learn faster while remaining statistically indistinguishable from normal behavior. Operating inside probabilistic confidence bands favors patience and subtlety, not brute force, and that asymmetry grows as sensing becomes more probabilistic rather than more precise. Defenders don't regain advantage through sharper thresholds or single measurements, but through aggregation, correlation, and time, by letting weak signals accumulate until probability hardens into evidence. And that's why the true quantum era shift is temporal, not computational. Attacks become quieter sooner, shrinking detection windows long before damage is obvious. In the end, security is never something you achieve once and move past. It's something you continuously negotiate with uncertainty because security is not a state, it's a process. Thank you for watching. If you found this useful, please like the video and subscribe to the channel. It really helps us keep building deep, real-world quantum security content. You can visit spectreai.ai to explore over 55 hands-on quantum security labs and learn by doing, not just by theory. If you're interested in going deeper, you can also find our books on Amazon. And finally, leave a comment and let us know what you'd like to learn next. We read them all. Thanks again, and we'll see you in the next video.